A common full Bitstream file is generally made up to the following components. A comment part or header stored mainly as the ASCII representation of the comment, reporting file name, creation date and time, and part model number. The header information does not need to be downloaded to the FPGA. Dummy words, with the purpose of aligning the parser on 32-bit word boundaries and a bus width auto-detection pattern, which is inserted at the beginning of every Bitstream. As we know, different FPGA families have different configuration interfaces. Each configuration interface corresponds to one or more configuration modes and bus width. Bus width auto-detection is transparent to most users, because all configuration bitstreams generated by the Xilinx tools include the bus width auto-detection pattern. These patterns are ignored by the configuration logic if the mode pins are set to master serial, slave serial, JTAG or SPI mode. A synchronization word signaling the upcoming of the actual configuration data is used to align the configuration data with the internal configuration logic. Within this context, no packet will be processed by the FPGA until the synchronization word will be found. Finally, the actual FPGA configuration. The FPGA configuration is basically made of a series of packets, with their respective headers, that are used to perform writes to the configuration register of the configuration hardware of the device, and a series of configuration words. The FPGA bitstream consists of two packet types, Type 1 and Type 2. Type 1 packets were the most common packet type in the configuration bitstream. Type 2 packets originally were used when the number of bits in the word count field of the Type 1 header was insufficient to count a big number of configuration words, data which was specified in the word count field. The Type 2 packet was created only for the purpose of reducing the overhead caused by the insertion of too many Type 1 packets in long writes to the same configuration register. Nowadays, the Type 1 packet is used for register reads and writes set by the value in the opcode field, and its header section is always a 32-bit word. Following the Type 1 packet header is the Type 1 data section, which contains the number of 32-bit words specified by the word count portion of the header. Looking at the figure, we can see all the 5 fields used to specify Type 1 packet header. With respect to what we have already described, it is worthy to mention that X is used to identify a binary digit, but which is actually used and contains important information, while R stands for a bit which is not used and reserved for future use. Within this context, the reserved bits should be set all as zeros. The Type 2 packet is used to write long blocks. The header section is always a 32-bit word, and the majority of the header of a Type 2 packet is used to store the count of the subsequent words. As we can see from the figure, no space is devoted to the register address, because it uses the previous Type 1 packet address. Therefore, a Type 2 packet must always follow a Type 1 header, and it can be seen as an extended word count field for the Type 1 packet. As it is for the Type 1 packet, following the Type 2 packet header is the Type 2 data section, which contains the number of 32-bit words specified by the word count portion of the header. Within this context, we can see that the significant data to understand the bitstream format are therefore in the header of Type 1 packets. In these headers, the opcode field is usually set to a null operation or to a write operation in configuration bitstream. When in write mode, the last 5 bits of the address field select one of the possible configuration registers, while the word count field indicates how many words the configuration logic must expect as a payload of the header.